Approximate integration with data. We now know that to find the area under the curve f above the x-axis from a to b, we integrate the function f of x with respect to x from a to b. This definite integral is the limit of the Riemann sum, the sum as I go from 1 to n, f of xi delta x, where f of xi is a functional value at an xi point in a representative ith interval, and delta x is the width of each of the interval. We also know that if we cannot find the antiderivative of the integrand easily, then we can estimate the definite integral using the left sum, the right sum, the trapezoidal rule, the midpoint rule, and the Simpson rule. Of all of these rules, the Simpson is the best estimate, and left and right are the worst estimates. Also, sometimes the function is not given, but we obtain the data or a table. If we have the necessary information, we should be able to use any of these rules to estimate the definite integral, which represents the area. From the diagram, we can create a table for the functions of the width in terms of xi. The width at x sub 0 is 0, the width at x sub 1 is 0.8, the width at x sub 2 is 0.5, and so on, all the way to the width at x sub 8 is 0.3. This is sufficient information for us to estimate the area of this small pool, whose widths are given at the interval of the length 0.6. They will measure 0.6 feet apart. We will estimate the area using the left sum, the right sum, the trapezoid, the midpoint, and the Simpson rule. Keep in mind that the Simpson rule can only be applied to even intervals. In this case, the I in xi go from 0 to 8, so we do have 8 intervals, which is even. In this case, delta x represents the length of each of the subintervals. Delta x is 0.6 feet, which was given. The width are now f of xi, where f of x sub 0 is 0, f of x sub 1 is 0.8, f of x sub 2 is 0.5, and so on. F of x sub 7 is 1.2, and f of x sub 8 is 0.3. These are the widths represent each interval. There are 9 numbers in the list, so we end up with 8 intervals. So n equals 8. We now plug this information into the formulas to estimate the area. For the left sum, L sub 8, it is delta x, which is 0.6, times the sum of the functional values using the left endpoints. They are 0 plus 0.8 plus 0.5 plus 0.4 all the way to 1.2 only. There should be 8 terms in the left sum. This is approximately 3.6 square feet. For the right sum, R8, delta x is 0.6 times the sum of the right functional values at each of the interval onlys, so we will start at 0.8 plus 0.5 plus 0.4 all the way to the last right endpoints, which is 0.3. This is approximately 3.78. For the trapezoidal rule, we take delta x over 2, which is 0.6 over 2, then 1 f of x sub 0, which is 0, plus 2 f of x sub 1, which is 0.8, plus 2 f of x sub 2, which is 0.5, plus 2 of each of the functional values between a and b, and the last term should be used only once, plus 0.3. This is approximately 3.69. We won't be able to use the midpoint rule in this case because we do not have the information for the midpoints unless we combine 2 intervals and make it 1. Each of these we would have the middle point, the midpoint. Using the Simpson rule, we take delta x divided by 3, which is 0.6 divided by 3, times the sum of f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3 plus 2 f of x sub 4 plus 4 f of x sub 5 plus 2 f of x sub 6 plus 4 f of x sub 7 plus 1 f of x sub 8. The pattern inside the sum is 1 4 2 4 1 or 1 4 2 4 2 4 1 or 1 4 2 4 2 4 2 4 1. This is the reason why we need an even number of intervals when we use the Simpson rule. This sum is estimated to be 3.86. Observe that the trapezoid rule is the average of the left and the right sum. It is true that the Simpson rule is the weighted average of 2 midpoint sum and 1 trapezoidal sum, but we don't have the information to find the midpoint sum in this case. Also, if we were to use this shortcut, then we would have estimated S sub 16 instead of S sub 8.